All right, so we have split the session, so I will take 10 minutes to show you a little bit more about Boston here in Germany, and then I'll hand over to Konstantin, and he will be talking about quality control in manufacturing by using modern AI frameworks. That's going to be a very interesting talk, I can promise you. So I guess you guys have heard about our other locations, and that we have locations all around the world, basically. I'm heading up our German operations. We are located a little bit outside of the city of Munich, in the southeast of Munich, where we have a what I call full facility in terms of we have our local build department here, a big central warehouse, German-spoken support and RMA, as well as our engineering team running our local Boston labs here. So what is the reason why people should be partnering with us here in the region? And there is a couple of elements which are especially important for HPC as well. So we are very fast and reliable, because we do work with all the major technology providers, also on a local level. So, for instance, the AMD lab is just like 5 minutes around the corner here. So if Konstantin needs to go into the AMD lab, he's there in 5 minutes. Intel is around the corner. Where we're really strong is customized configurations. We'll go into a bit more detail in a second. And of course, we do all the system integration and if needed, installation services around the solutions. We have a very strong pre and post sales team supporting you in your projects. We help you evaluate and optimize to find your best solution. We take care on infrastructure and management, as well as the global stock keeping and the logistics, which is even more important now during the pandemic and the global shortage. We run the Boston labs here. I haven't mentioned that yet, but we are following a first to market strategy, meaning that we always try to be first to market with the latest and greatest technology. Of course, we tried in our labs first at a very early stage, and then also provide customers with access to this technology to find out whether this is a good fit for them and their projects. And then we have the Boston Training Academy, where we offer a good number of training courses to customers. And Konstantin is one of the trainers there as well. So how do we work during a project? So we start out with normally with our engineering team or the pre-sales team and go into the analysis of the requirements. Once we know what the exact requirements are and we have fully understood them, we can offer, if necessary, a test setup and a proof of concept in our labs that people can actually try the platform and test it. Then we check it against the budget, of course, and see if it fits into the costs. Like I said, we offer a big number of customization options, like different colored front bezels, customer logos, special documentation, of course, benchmarking for HPC clusters and stuff. And then we offer delivery and installation services, as well as global warranty in terms of on-site services if necessary. And then we are at the end of the life cycle of the systems, where we need to take care on the recycling of the systems. Values around that are the warranty services, as mentioned, the Boston labs to try out things, the training academy to train up your staff, and then we do offer financial options like leasing and financing. This is our portfolio from small to big, if you like. So we have all kind of different form factors and server systems, from single node to multi-node to blade systems, loads of storage. Systems can be air-cooled, direct contact, liquid-cooled, immersed-cooled, can be can be either 19-inch or 21-inch, so open compute project where we have our own product range. Again, here all type of cooling available. You always get complete freedom of choice, no matter if you want to go for, let's say, AMD CPUs, Intel CPUs, IBM Power or ARM, or you have any favorite hard drives or RAID card manufacturers. I will not bore you with the references here, but just to show that we're working across all different verticals. So we're in all industries active. And I'll finish with 3 little case studies. So this is one which is a GPU HPC cluster we did together with ARCO, or better known as Fendt, so the tractors you see here. So this is a fully managed, in that case with Bright Cluster Manager, and supported cluster installed by Boston. Then we have an example of a fully immersed liquid-cooled HPC cluster we rolled out for the Goethe University in Frankfurt, the Loewe Institute. A very nice and very powerful installation. As you can see here, we squeezed out 40% more CPU performance over the air-cooled solution. And the third one is a industrial edge application we designed together with the German Edge Cloud, which is a retail company, for their smart factory solutions. So this is just a little snapshot of our, well, this is actually a current project here. We're currently rolling out 1,300 server nodes for the big accelerator in Switzerland at CERN, as well as close to 5 petabyte of storage capacity. So these are just a couple of examples of current projects we have been doing lately in the space of HPC. And with that, I'd like to hand over to Konstantin for his quality control in manufacturing talk. Thank you very much.
So, dear ladies and gentlemen, also a warm welcome from me to the second part of this talk. I will talk about quality control in manufacturing using modern AI frameworks. We are aiming to help small to medium-sized businesses that are the backbone of the German economy. Many of them are strong in the manufacturing space, sometimes being world leaders. There is a greatly underused potential for digitalization and modern AI methods. They employ many great engineers that do not come from a software background. So these companies need AI that does not require deep software engineering skills. One of the tasks that is part of nearly every manufacturing process is quality control. Quality control is an important but often labor-intensive and mundane task. It is a problem we would like to hand to a computer, but there's a common misperception that AI is expensive and difficult to implement into manufacturing processes. Our strategic partner NVIDIA develops a lot of easy-to-use software to help non-software engineers to access the power of AI. Our main goal as Boston is to help our customers to enhance their productivity. I will give a brief overview of an NVIDIA AI framework and a case study that was conducted on quality control in steel welding. This is NVIDIA's standard workflow for deploying AI in a production environment. It describes how to get insights from raw images. Sensors deliver data, the data then gets pre-processed and used within NVIDIA AI frameworks for inference. This all happens on the so-called edge, inside the Internet of Things sensors or in close proximity, maybe an on-site server. These insights gained can be used to steer manufacturing processes with a low latency. For training and analysis, the data is then moved to a data center. Statistical analysis, re-evaluation, and retraining of the AI algorithms can be done at the data center. We can then finally use the gained insights for strategic decisions on planning our manufacturing processes for the future. In this talk, I want to focus on the NVIDIA Transfer Learning Toolkit, short TLT. The goal of TLT is to speed up the development process of production-ready AI solutions. The labeling of data is expensive. Pre-trained and optimized models do provide an advantage in training time, and they do require less labeled data to give accurate results. So you save time and money over there. Tuning and pruning is simpler with TLT due to a great amount of it being already part of the default TLT setup. This normally delivers great results. Nonetheless, within TLT, we can refine many hyperparameters to deliver the best possible results. Deployment in a production environment is easier when using NVIDIA DeepStream SDK and Jarvis compared to a manual deployment. NVIDIA TLT can be obtained for free and is meant to be used in commercial applications. There's no licensing cost. TLT comes inside a Docker container, making deployment and scalability easy. No more worries about dependencies. It can be invoked from a Jupyter notebook. Some great example notebooks guide the way to your first successful deployment. This helps domain experts immensely to use AI in their projects. NVIDIA has a software hub called NGC. The NVIDIA GPU cloud is not a public cloud. It is the place where you can obtain the Docker images and optimize neural networks. We mount our training data into the container. And then we start the cycle of training, evaluating, and pruning. When we are satisfied with the accuracy, we export our model, either as a normally trained model, or we can put it into an int8 calibration flow to even prune the model even further. Most of the commands used within TLT use configuration files. These are filled with default parameters and default strategies, like for instance a learning scheduler. In the configuration file, we point to our train, validation, and test data sets. In the training section of the configuration file, we specify the hyperparameters for the training of the neural networks, like for instance, the network architecture, learning rate, and regularization. There are many more parameters and strategies we can configure. The evaluation process of the neural network has to be also configured. NVIDIA TensorRT is part of NVIDIA TLT and is meant to optimize the inference performance of a neural network after it has been trained successfully. TensorRT allows to increase the throughput and lower the latency through a set of techniques. Maximize the throughput by quantizing models to int8 while preserving accuracy. Optimizes the use of GPU memory and bandwidth by combining nodes in a kernel. Select the best data layers and algorithms based on the target GPU platform. Reduce the memory footprint by reusing the memory for tensors efficiently. Use multiple streams in parallel. For recurrent neural networks, optimizations across time steps can be achieved by using dynamically generated kernels. I now want to demonstrate the power of NVIDIA TLT by looking at a data set that describes defects that occur during steel welding. Steel welding is a process to connect two steel plates and is of fundamental importance for many manufacturing processes. It is a challenging process that requires skilled craftsmen or advanced machinery. The dataset contains images of welding process, and our goal is to classify if a weld is good or faulty. The following errors are classified: burning through the plates, contamination, lack of fusion gas, lack of shielding gas, or too high travel speed. The dataset we are using is freely available on Kaggle, a platform for deep learning education and challenges. It contains around 45,000 images and was created by researchers at the University of Birmingham. On the right side, you can see an exemplary image. The image is uploaded in a grayscaled and landscape orientation. In this study, you want to see what kind of insights we can get from this dataset using NVIDIA TLT. This does give us some great savings, especially regarding development time. In deep learning, the data quality is really important. The data quality refers to the images, but also to the labeling of the data. Labeling can be difficult if, for instance, a weld is still okay, but starts to show first signs of an error, or an image displays multiple errors. Because of this, labeling has to be done by domain experts. For our study, we will use a standard classification approach that's based on pre-trained ResNet models. The dataset is split into a train, evaluation, and test set. On the left side, we can see the data distribution in the test dataset. The dataset is distributed unevenly, with good weld having about 75 times higher occurrence than lack of fusion gas. Than the lack of shielding gas. This is typical for real-world data collection. Some errors are rare, but can still have a severe impact on the strength of the weld. As this is a general HPC conference, I would also like to talk a bit about performance metrics for deep learning models. After the training has finished, we evaluate the final neural network with the test dataset. There are 4 possible outcomes for the evaluation of a single class. Positive means it's part of the class. Negative, it means belongs to another class. For a single class, we can then look at the number of images that are true positive, true negative, false positive, or false negative. For every class, we then calculate KPIs based on ratios of its different classification results. There are three widely accepted precision metrics: precision, recall, and F1 score. Precision is defined as true positives divided by the amount of predicted positives. This is a good measure when the cost of a false positive is high. For instance, to accept a world as a good world, even if it's actually bad. Recall is defined as true positives divided by the amount of total actual positives. It is a good measure when the cost of a false negative is high, for instance, a corona test. The F1 score is the metric that combines both together. Depending on the process and how quality control is implemented, we have to adjust our priorities, but in general, we would like as little false and as many trues as possible. The optimal scores are 100% for all KPIs. I now want to present the results from our small study. We use ResNet as our neural network. Many hyperparameters can be tuned. Here I want to present the results as a function of the network size. The number behind ResNet determines the number of layers of the neural network. In general, we can say that a deeper neural network should understand more substructures and deliver deeper insights on the images. However, this is not always true. Sometimes the neural network starts to find artifacts which do not correlate to features of the classes, but depend on noise in the images. The precision in the class good world is excellent across all three networks. The other values are also quite good with a few exceptions. So it seems it is not easy to find what is the best neural network. Looking at the averages, we can see that the decision should be made either between ResNet 18 or ResNet 50. The circles are surrounding the problematic values. The arrows symbolize where the pictures that were not identified correctly were put instead. For ResNet 18, some burn-through and contamination images are classified as lack of fusion gas. For ResNet 50, some of the good wells are wrongly classified as lack of fusion gas. It seems as our neural networks have problems describing the lack of fusion gas correctly. So what is the best neural network? Well, it depends on what you want to do with your network. ResNet 18 seems to be a more stable neural network. ResNet 50 could see better results if the difference between good wells and lack of fusion gas could be made clearer to the neural network. This could be achieved by manual data augmentation between the classes or potentially acquiring new data. We now want to compare our results to previous work on a dataset. The researchers that created the dataset are from the University of Birmingham, and they published a peer-reviewed paper on it in 2019. The best values for every row are marked in green. They used custom network structures and some custom data cropping and transformations. We, on the other hand, use pre-trained ResNet and let all the data loading, transformation, and augmentation to NVIDIA TLT. Our development time is mostly spent on training evaluation. For a better overview, we use the F1 score on this table. The researchers use two different kinds of networks, one based on fully connected layers and one on convolutional layers. Their convolutional networks gives good to okay results for most values, but fails completely at the recognition of lack of shielding gas. Their fully connected network performs worse on average, but can detect some of the lack of shielding gas. However, it struggles with burn-through and with high travel speed. Both networks have bad macro averages. These neural networks should not be used in production environment. Our networks, however, have excellent scores. The ResNet 18 is the more network in general. ResNet 50 has the earlier described problems to determine between lack of fusion gas and good weld, but this could be covered by manual after control for discovering the wrongly classified lack of shielding gas. I now want to conclude my talk. We need to understand the problem we try to solve. We need to democratize AI and bring it to developers and engineers. Data quality is key. Try to keep the environment of the measurement as constant as possible. Do not try to reinvent the wheel. Make use of frameworks such as NVIDIA TLT. NVIDIA TLT allows for a more robust, faster, and less cost-intensive AI workflow. Multiple cycles of data collection and analysis promise the best results. You can then try to find the weak spots of our neural network and collect data that tackles the weak spots. We as Boston hope to be part of your AI journey. If you have interesting projects or would like our help, feel free to contact us under the following email address. Thank you for your time.